All right, good morning. Again, the test will be made available later on this morning, and just sort of wrapping things up. Okay, and we have just picking up where we left off. Okay, with the test two review set, and we have with the first part. Again, we left off with the first three parts in number 17 from the first portion in the review. Okay, and we had for the domain of the sum difference in product functions that we had for f of x and g of x to end up with this particular set of subintervals. Now, in the case of what we have regarding the quotient function, okay, so we have in part D on this one, okay, so we have for f over g of x, okay, and so looking at expanding, okay, so we have f of x over g of x. Okay, now with the sum difference in product functions, again, the domain is on the basis of the combined restrictions for f of x and g of x. And you're still going to be combining the restrictions for the quotient function, but you still might have yet another restriction once we get to the end result, okay, for the quotient function. Okay, so we have, again, right now to keep f of x defined, again, we have that x cannot be equal to 1. And to keep g of x defined, again, g of x is its own rational function, and to keep the denominator from equaling 0, okay, we have that x cannot be negative 12. And we have in the setup in following through, okay, so I have a fraction over a fraction, and undoing the division by x over x plus 12, okay, I can just multiply the top fraction by the reciprocal of the bottom fraction. And for what we will have in this development, okay, so we have 3 times the quantity of x plus 12 all over, and you can say x minus 1 times x, or x times the quantity of x minus 1. And again, we already have established that x minus 1 cannot be 0. X already from x plus 12, which was originally in the denominator, cannot be at negative 12. And now that we have flipped g of x, we now have x now situated in the denominator position, so x cannot be 0. So for what we have in the case of part D, okay, so we have in the case of the domain, so we're leaving out negative 12, 0, and 1. So just kind of providing somewhat a visual for what we have here. Okay, so we have values left out at negative 12, 0, and 1. Okay, so we have, again, so negative 12 is excluded, 1 is excluded, and 0 is excluded. And just looking at what we have on a visual basis. Okay, so have line segments in the middle, and then for the far extremes, okay, we have rays upon which one is going to go continuously to the left and the other continuously to the right. And so for what we're going to have in the case of the domain, okay, so for the lower end, okay, so we have going from negative infinity, approaching but not including negative 12, And then we have going past negative 12, approaching 0, but not including 0. And then we have bypassing 0, going past that, and approaching but not including 1. And then for the rest, okay, we have those values of x that will be greater than 1. All right, and so we have 3 exclusions from the domain of the rational function. Okay, so we have 4 subintervals that are formed, whereas with the other 3, again, we had only 2 exclusions from which we had these 3 subintervals. But now, again, we have an added subset thanks to the exclusion of 0 in the case of the quotient function. Now, for what we have in the case of parts E and F, okay, now we're looking for the domain of the compositions, where in part E we have F composed with G of x. Okay, so now we have in compact functional notation case, so we have F of G of x. And okay, so we have in the way that the order between f of x and g of x, or f and g, are displayed, okay, we have the output function in line with f, okay, and f of the input, again, we have 3 over the input minus 1, okay, and now we have with g of x as the input, okay, so you're going to have f of x equal to 3 over g of x minus 1. And so just filling in the variable expression that defines g of x. So again, g of x, we have x over x plus 12. You have minus 1. Okay, so I have a bit of a complex fraction where I have, not in the sense of the letter I, but where I have a ratio where you have fractions in the numerator and or denominator. Okay, so just to clean this up, okay, so I'm going to multiply this ratio by 1 in the form of the denominator that's creating this complex situation all over itself. Okay, so you have 3 all over, and you have x over x plus 12 minus 1, and again we're going to multiply by 1 in the form of x plus 12 over itself. Okay, and so just carrying on, okay, with what we have here, so you have 3 times x plus 12. And to show you the dynamics that will be created, okay, where the denominator terms are concerned. So we now have, you have x over x plus 12. And that's going to be multiplied by x plus 12 in the denominator. And we have minus 1, and negative 1 is going to be distributed also over this x plus 12. Okay, so for what we have here, you got 3 over x plus 12. Now in the denominator, you have x over x plus 12 multiplied by x plus 12. So if you think along the lines of cross multiplying, so you have x plus 12s are going to go out. So for what we have at this stage, okay, so we have 3 times the quantity of x plus 12. And we have all over x. And guess what? We have negative 1 over the quantity of x plus 12. So this would be minus x minus 12. So we have x and negative x. Okay, those are going to cancel each other out. And we have 3 times the quantity of x plus 12 all over negative 12 And you can reduce this because 3 over negative 12 reduces to 1 over negative 4. So we can say that we have in the output, okay, we come out to x plus 12 over negative 4. Okay. And now, in looking at the domain for what we have here, okay, so again, you have, again, two primary characteristics about the composition of functions, again, to focus upon in order to find out the domain. Okay, so for the input we have at g of x and g of x, okay, we have equal to x over x plus 12. And again, the only restriction for g of x, okay, we have that x cannot be negative 12. In the case of the output, okay, for the output, okay, so you have x plus 12 over negative 4. Now we have a fraction, but in the denominator we have a non-zero value, and it's going to stay as such. And the only location for x is in the numerator, so the numerator can be zero value as long as the denominator does not equal to 0. So in the case of the output, again, we have x plus 12 over negative 4. Now this particular part has no restriction. Okay. And then now for the whole composition, okay, and I mean no restriction as in no added restriction, but the restriction for the whole thing, you're looking at combining what we have for the input function and what we have in the output result. So the only restriction is going to be from the input. Okay, so we have the x cannot be negative 12. Okay. And so for what we're going to have for the domain of f composed with g of x, okay, so you have centered around negative 12, which once again is excluded. And for the activity, okay, so you have to the left and also to the right. Okay, so you have one end, okay, approaching negative infinity and the other positive infinity. And so we're going to have for the domain, going from negative infinity approaching but not including negative 12. And then we have, for the rest of the set, you have those values of x greater than negative 12. And again, so we have the exclusive use of parentheses for the interval notation in expressing the domain. Okay. Now, for what we have in the other composition, okay, whereupon we have g composed with f of x. Okay, and this is a little bit tricky too. And again, just for the compact notation, okay, so we're looking at taking g of f of x. Okay, so you have the input with f of x and the output we have in line with g of x. So we have g of the inputs, again, we have the input divided by the input plus 12. Okay, so we have with the inputs at f of x, so again, we have the input divided by the input plus 12. And just filling in, okay, now for that upon which f of x is set equal, again, we have 3 over x minus 1. And we have all over, okay, we have 3 over x minus 1 plus 12. Okay, and just as I had cleared out x plus 12, I'm going to clear out x minus 1. Okay, so we have, for the expression case, you have 3 over x minus 1, you have all over 3 over x minus 1 plus 12. So I think I'll do this. Okay, so you just have rewriting this ratio. Okay, so I'm going to multiply this ratio by 1 in the form of x minus 1 over itself. Okay. Okay, so I have 3 over x minus 1 times all of x minus 1. So we have the x minus 1s to clear out. And for what we have in the case of the denominator, okay, so you have 3 over x minus 1. We have times the quantity of x minus 1. Okay, so the x minus 1s here are going to clear. And we have plus 12 times, okay, the quantity of x minus 1. And so we're going to have in the rewrite, okay, so the numerator, okay, this will become 3. And we have all over, now we've got 3. And 12 over the quantity of x minus 1. So this is going to be 12x minus 12. And combining the constants in the denominator. So we're getting it narrowed down to where we have 3 over 12x. 3 minus 12 becomes negative 9. And since we have a common factor with 3, okay, 3 over 12x minus 9, that can be lowered to 1 over 4x minus 3. So we have in the simplified form, okay, that would be the result whenever we have g composed with f of x. Now, where we have the domain to be concerned, okay, so again we have before the input function was g of x, now the input function is f of x. Again, so for f of x, we have 3 over x minus 1. Again, we have for the restriction, okay, we have the x cannot be equal to 1. And for what we have in the case of the output, okay, we have 1 over 4x minus 3. Okay, and since we have a fraction, whereupon we have 4x minus 3 in the denominator, okay, there does lie a restriction with the output that 4x minus 3 cannot be equal to 0. So we have that 4x cannot be equal to 3. And with division by 4, okay, it turns out that the restriction upon just the output portion is going to be the exclusion of 3/4. Okay, so we have just combining the restrictions. So for g composed with f of x, again we have the x cannot be equal to 1. I also have the x cannot be equal to 3/4. Okay. And so just looking at what we have here. Okay, so you have two restrictions from the domain, okay, and they are in close proximity to each other. Like 3/4, which is like 0.75, and you got 1. Okay, both of these values are excluded, so you have holes at the locations. Okay, and once again, you have rays going in opposite directions. And you have the continuities at the opposite extremes, okay, negative and positive infinity being those extremes. So for g composed with f of x, okay, so you're going to have, in the case of the domain, okay, so you have going past negative infinity, approaching but not including 3/4. Again, bypassing 3/4, so we have for the middle strip, have those values of x greater than 3/4 and approaching but not including 1. And then we have for the rest of the set, we have those values of x greater than 1. Okay. And once again, we have use parentheses exclusively as the grouping symbols, okay, in defining the domain in terms of interval notation for g composed with f of x. Okay, and those were complex problems. Now, in the case of what we have regarding the second part, okay, of the review. Okay, so we still have looking at for the first three items. Okay, so we're looking at domain once again, and okay, so we have for number one, we have just a rational function. We have x minus 1 all over x squared minus 4x plus 3. Now again, technically f of x is a reducible fraction because you would have a common factor with x minus 1 in both the numerator and denominator. But do not think along the lines of canceling or reducing to get to the domain. Again, for rational function, okay, you're going to consider the entire domain in its original presentation in terms of finding the exclusion. So don't think of reduction, and go ahead and find out everything. Everything that is restricted comes from all the factors in the denominator, regardless of whether they can be canceled or not as the ratio is reduced. So we have, for this one case, we have the denominator. We have x squared minus 4x plus 3 cannot be equal to 0. And looking at factoring, okay, so for x squared minus 4x plus 3, okay, we'll have with our binomial factors, so we have x minus 1 and x minus 3, and neither factor can be 0 in value. Okay, so you have the x minus 1 cannot be 0, from which x cannot be equal to 1. As for x minus 3, okay, if that cannot be 0, then we have the x cannot be equal to 3 either. And so we have, okay, just with the exclusions, again, we have both 1 and 3 left out. And once again, we have with the activities, okay, so you have with the rays, okay, you have going in opposite directions. And so for the first item, okay, so you have with the domain, so you have going from negative infinity approaching but not including 1. Then we have going between but not including 1 and 3. And for the rest of the domain, we have those values of x that will be greater than 3. Okay, so that will be the result of what we have in the first problem in the second part of the test review. And for what we have for the second item, okay, you have just g of x is equal to 2x squared over x plus 5. Okay, so you have another rational function, and there is only x plus 5 in the denominator. And we have that x plus 5 cannot be equal to 0. Okay, so we're going to have the x cannot be equal to negative 5. So you have only negative 5 is excluded. Okay, so you have a hole at negative 5. And the only activity, there's no line segment in this instance. I have just one exclusion. You'll just have instead rays going in opposite directions if you put the results in terms of graphing. Okay, so you have one ray going to infinity, the other to negative infinity. And so for what we have in the case of the domain, okay, so you have those values of x less than negative 5, along with those values of x that will be greater than negative 5. Okay. And we have in the case of the third item, now we have h of x is equal to the square root of 9 minus 5x. And for this one, okay, all right, for the square root of 9 minus 5x, okay, now I have the radical given in direct terms. There's no fraction. So 9 minus 5x can be 0. And since the restriction comes only from the square root portion, okay, we have that 9 minus 5x cannot be negative. Now it can be 0 and it can be positive. So you have 9 minus 5x will be greater than or equal to 0. And in isolating the variable term, so if I take 9 away from both sides, so negative 5x is greater than or equal to negative 9. And we have with division by negative 5. Okay, again, if you multiply or divide by negative, the direction of the inequality is going to change. And for what we have in this instance case, you're going to have the x is less than or equal to, and a negative over negative is a positive, and we have 9/5. Okay, and just for the domain here, okay, so we have defined by x is less than or equal to 9/5. Okay, and 9/5 is included in case you have a solid point. And from this, the only activity occurring, okay, is going to be a ray going out to the left. And we have the lower limits tending to negative infinity. So we have, in the case of number 3, we will have for the domain, okay, so we have those values of x going from negative infinity, and we have approaching and including the value of 9/5. And thanks to the inclusion of 9/5, around that number is going to be a bracket. All right. Now, for what we have in the case of the fourth item, okay, so this is again, you're looking at the average rate of change, and average rate of change. This is just a formal way of saying what we're going to we're asking what the slope is going to be. And we're looking at the average rate of change going from x equals -1 to x is equal to 4 given this particular function. And for what we have in the case of 4, okay, so we got the function. So we have f of x is equal to -3x squared plus 2x plus 1. Now, for what we have at x is equal to -1, okay, so we have that y is equal to f of -1 so we have -3. Okay, so we got -3 times, okay, the square of -1, and we have plus 2 times -1, followed by the addition of 1. Okay, now the square of -1 is going to be positive, and I'm still going to multiply by -3, so I have -3 times 1, and we have, following, we have 2 times -1, so we have a -2. Again, we have followed by the addition of 1. So we have -3 minus 2 plus 1. -3 minus 2 is -5. -5 plus 1 is -4. All right, so just looking at what we have here. Okay, so we have a point on the graph of this function. Okay, so when x is -1, your corresponding y value is going to be at -4. And for what we have with our second point, so we have at x is equal to 4. So we have y is equal to f of 4. And we have is equal to, now for -3x squared, okay, we have -3 times the square of 4. Then you have plus 2 times 4. Followed by the addition of 1. So we have -3 times 16. You got 2 times 4 is 8. We have plus 1. Okay, so we have -48 plus 7, or plus 8 plus 1. Okay, so -48 plus 8. Okay, we're going to have made that, or plus 9. Okay, so you have -48 plus 8 is -40. -40 plus 1 comes out to -39. Okay, so we have a point through which this graph is going to pass, and we have whenever x is equal to 4, the corresponding y value. Okay, we have at -39. Okay, so for the average rate of change, again, okay, you're looking at going from where x is -1, okay, we're going from the point -1, -4, to where x is equal to 4, where we had the point at 4, -39, okay. And for the average rate of change, okay, so average rate of change. So you're looking at the slope, and now the graph of the function is not a straight line, but if I have a straight line to cut through these 2 points to find out, okay, just what the average rate of change is going to be for this immediate slice of the pie, so to speak. Okay, you're going to have, again, the line that cuts through those 2 points is going to be the secant line. And again, just for the formalizing, okay, so you, again, you have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. But since I have the specific coordinates, I can just put this in the context of the traditional slope formula, whereupon we have y of 2 minus y of 1 is all over x of 2 minus x of 1. And so just filling in the values. Okay, so since I have the first point at x equal to -1, let's say that we have the first x and y values will be -1 and -4. And with the second set of x and y terms, okay, we'll say we have that for 4 and -39. So we have in the follow through, so for y2 minus y1, so we have -39. And we have subtracting y1, which is going to be at -4. And for x2 minus x1, so we're going to have 4 minus -1. Okay, so -39 minus -4, that's like -39 plus 4, so we have a -35. 4 minus -1, okay, that is going to be at 5. And for the average rate of change, okay, that is going to be an integer value. For 5 goes completely into -35, -7 times. Okay, so between these 2 points, not for the whole function, the slope of the function is going to be continuously changing, but for the snapshot, connecting -1, -4 to 4, -39, and is that at that moment in time that the average rate of change comes out to -7. Okay. All right. Now, regarding what we have for odd and even functions, and to test out whether we have the given function is odd, even, or neither. And just kind of going back, again, we have for odd and even functions, again, for an odd function, if we have opposite sign inputs to lead to opposite sign outputs. So in this case, we have f of -x is equal to the negative of f of x. Again, opposite sign inputs lead to opposite sign outputs. Now, in the case of an even function, okay, what's going to happen here is that if you have additive inverse inputs, you're still going to come out to the same function value. And for what we have in the case of number 5, looking to see whether we have this function to be odd or even or neither. Okay, so we have given, we have that f of x is equal to x times the absolute value of x plus 5x cubed okay. And so for what we have here, okay, so we're going to test this out and see how it compares with f of -x. Okay, so looking at the spread, okay, so we have for f of x, okay, so you have x times the absolute value of x plus 5x cubed. Okay, now for the absolute value of x, or just say that is equal to x. And for f of x, we can say we have x times x plus 5x cubed and so that is going to become x squared plus 5x cubed. Now, for f of -x, okay, so just putting in -x in place of x, okay, so we got -x, we have times the absolute value of -x, and we have plus 5 times the cube of -x. Okay. All right, so just some things here. Okay, now, just like the absolute value of a positive is a positive, the absolute value of a negative is also positive. So the absolute value of -x is going to be at x. And for the cube of -x, we have a minus x cubed. So here we're going to have x for x. Okay, so you have so you got negative x times x and we got plus 5 times negative x cubed Okay, so you have negative x times x, so we have negative x squared, and 5 times negative x cubed, so we have minus 5x cubed. Okay, now I'm just going to repeat the output from f of x, so we have x squared plus 5x cubed. Okay, so just taking what we have here, so with the inputs, okay, these are opposite. If you notice with the output, okay, we have exclusively positive terms for f of x, whereas in the case of f of negative x, these are exclusively negative. Okay, so we have in the lineup, okay, we have the terms to be opposite throughout. And if an opposite sign inputs lead to opposite sign outputs, we're going to have the case of an odd function. What you can do is that you can kind of do a quick sketch. So you have like x times the absolute value of x, you have plus 5x cubed. Now for the graph, you're going to have symmetry with respect to the origin. Okay, and just putting this in table terms. Okay, so again, opposite sign inputs lead to opposite sign outputs. If you notice for -1, -6, I've made this into a +1. Like over here, you're going to have a +6, and also we have -2, -44, 244, and for the next item, let's say if I have the next input is at -3, you got -144. If the function is odd and I put in 3, I'm expecting a positive 144, which I'm going to get. So opposite sign inputs will lead to opposite sign outputs. Okay. Now, so I have an odd function in the case of number 5. Now for 6, I have g of x is equal to 2 over x plus 3. Okay, so I have g of x is equal to 2 over x plus 3. And so we have with g of x, okay, so I have 2 over x plus 3. And for g of negative x, so if I replace x with negative x, okay, so 2 over negative x plus 3. Okay, now the inputs are opposite each other. Okay, if you notice you have 2 over x plus 3, 2 over negative x plus 3. Okay, so okay, we don't have the same terms. The outputs are not the same. And okay, now here I have a positive fraction. And now the opposite sign of 2 over x plus 3 would be like the equivalent of the negative of 2 over x plus 3. And if I situate the negative sign in the numerator, this would be like -2 over x plus 3. But if I shift the negative sign to the denominator and keep 2 positive, the negative of x plus 3 should be -x minus 3. And so in this one, okay, you have the outputs are neither the same nor opposite. And so in terms of whether the function is odd or even, it happens to be neither case. And just like, say, with the rational function case, you have y is equal to 2 over x plus 3. Okay, if you notice, you don't have any symmetry with respect to the origin, nor do you have it with respect to the y-axis. And again, if I take, say, opposite sign inputs, okay, if I had odd and even functions, the outputs should have the same absolute value. If you notice, you have -1, 1. And if I had an odd or even function, the output for x equal to 1 should be 1 or -1. But if you notice, you got 2.4, undefined, 1/3. So this is kind of going all over the place. And so there's no pattern that suggests at all that the function is odd or even. So 2 over x plus 3 falls in the category of being neither odd nor even. Okay, and for what we have in the case of h of x, so we have the cubic root of x to the third plus 5x okay. And so for what I have here, okay, so I have a radical function so we have the cubic root of x to the third plus 5x, and if I insert for the input -x, so here I'm going to have the cubic root of the cube of -x. And we have plus 5 times -x. Okay, so right now we'll have the cubic root. Okay, so I got -x cubed minus 5x. And say if I factor out the negative, okay, so you have the cubic root of what is going to be the negative of x cubed plus 5x. And what's going to happen here, say like you got the cubic root of -1 times the cubic root of x cubed plus 5x. And so from this cubic root of a negative, so I'm going to have the negative of the cubic root of x cubed plus 5x, whereas with what I had with h of x, we say that is going to be the positive cubic root okay, so we have the positive cubic root of x cubed plus 5x. Okay, all right, so we have in this case you have opposite sign inputs, and for the outputs, okay, you have like positive cubic root of a term, the opposite is going to be the negative. So these are going to be opposite, and so since an opposite sign input leads to an opposite sign output, okay, just like number 5, this particular function we have in number 7 is going to be odd. Okay. All right, and once again, just see if I can get this on display here. So you have y is equal to, and see if I can find that radical. Let's see. Yeah. So you have the cubic root of x to the third plus 5x. Okay, so it's like we'll have symmetry with respect to the origin, but again, for odd functions, we have opposite sign inputs will lead to opposite sign outputs. Okay, if you notice, okay, we have -1, 1, -2, 2, -3, 3, -4, 4 opposite sign inputs. Notice we have opposite sign outputs. Okay, so the outputs for inputs that have the same absolute value, they're also going to have the same absolute value. And again, we have this function to be 1, that is an odd function. For what we have in the case of number 8, okay, so we're looking at a graph. And I'll tell you what I'm going to kind of do here. Let's see if I can. Okay, so for this particular part, it says that for the graph below, it says to determine the domain and the range, as well as the relative maxima and minima, and also where the relative maxima and minima occur, and also the intervals where g of x is strictly increasing, and the intervals where the same function is also strictly decreasing. Okay, now for what we have on the side of the domain and the range. Okay, now with domain, okay, now the fixation is going to be with the activity regarding x. And if you notice, we have with the arrowheads, okay, so you have where they're pointing. Okay, now this is going to suggest that in terms of the motion regarding x, you kind of have the left one you have just kind of slowly drifting further to the left, approaching negative infinity, whereas with the other, you have just kind of drifting incrementally and running continuously to the right and approaching infinity. Okay, and if you notice, so if I were to read in order from left to right, so you have going from negative infinity and going down to the left, and so everything, so this graph is running continuously. There's no hole, there's no location of any discontinuity, and then we have and it turns out that toward the end, okay, as we go farther up and out to the right, we have going out, approaching x at the continuous end, where we have approaching infinity. Okay, so we have for the domain, okay, that's going to be the set of all real numbers. So you have going from negative to positive infinity. Now, from what we have in the case of the range, now we're not going to have the set of all real numbers on this. Now, for the range, okay, you're looking at just the values in y. I'm going to use like the red to indicate the vertical situation. Okay, so we have like at the ends here, you have approaching y going to infinity. Because you have continuous upward motion. But for what we have at the lower end, okay, so you have from y infinity, and once the function is going down, okay, now it's going to bottom out at this point. So you have the lower limit in the range. We have at y is equal to -5. Okay, so the minimum value of y is going to be negative 5. And the upper can have everything else greater than negative 5 in y. So for the range, we're going to go from and including negative 5 and approaching infinity, and with negative 5 included, and the solid point is kind of an indicator. So we're going to have negative 5 in the bracket, and again, infinities are boundless, so that is going to be in the parentheses. All right. Now, where we're going to have the relative minimum and maximum to occur. Okay, so still working with the same graph. So you got the domain and the range already laid out, and I'm just kind of give you, well, we have for this one. Okay, so you have with the ordered pairs. Okay, so you're going to have relative maximum. And the relative maximum or relative maxima, well, it's going to be maximum since we have just a single point, but anyway, okay, now the relative maximum will be in reference to the y values. Okay, so for the maximum here, okay, the order pair we have at 2, 1. Okay, so the relative maximum is going to be the y value for this point, and so that is going to be at y is equal to 1. And now where the relative maximum is going to occur, that's going to be your x value. In this case, your corresponding x value is going to be at 2. So it's going to occur at x is equal to 2. All right. Now, for what we have regarding the minimum, okay, those are where you have the location where you have the graph to bottom out, where a decrease is followed by an increase. Okay, so for the relative minimum, okay, those are going to be your y values. Okay, and it doesn't matter what order you place them, but here, okay, with the relative minimum, okay, so you have y at negative 5. Okay, that's our bottommost point overall. And we have the other minimum, okay, so we have at y equal to negative 2. And the relative minimum, okay, where they're going to occur, okay, we have for the corresponding x values. Okay, so when y was negative 5, we had x at negative 1. And when y was at negative 2, the x value was at 4. Okay. Okay, so the relative minimum will occur at x equal to negative 1 at this point, and also at x equal to positive 4 at that point. All right. Now, in terms of the intervals, decrease and increase. Okay. And again, so we're looking at the action or the flow of the pattern for what we have in x. So we have the left extreme we have tending to negative infinity, right extreme we have tending to positive infinity. And just in the pattern, okay, so reading order from left to right, so you have a downward trend until we get to this relative minimum. So you have, so you got a decrease for this initial bit of activity, and then after you get to the relative minimum, okay, we have followed by an increase. And of course, after you get to this only relative maximum, okay, we have a decrease is going to follow. And again, after we get to the second and last relative minimum, okay, the graph is going to rise. Okay, so you're going to have an increase that's going to run continuously from here on out. So for what we have in the case of for the intervals of strict increase, Okay, so for the intervals of strict increase, okay, so where we have increase to occur, okay, so after we get past this first relative minimum, okay, so we have going past x at -1, and the function increases until we get nearer to x is equal to 2. So you have between -1 and 2. That's for the first increase, and then for the second and last indicator of increase, so we have going past x is equal to 4, and again we have running out in the direction of where x is going to be tending to infinity. So the intervals of strict increase, you have again describing these two specific graphed portions, and for the intervals of strict decrease, okay, this is where we're going to have the downward trend. Okay, so for the first decrease, okay, so you have going from -infinity approaching, again, the relative minimum at -1, -5. So you have going from x at -infinity approaching, but not including x is equal to -1. So you're going to use for the increase and the decrease, again, we're going to be using parentheses in the interval. So we have from -infinity approaching -1, and then we have with the second and last activity of strict decrease, so you have between this relative maximum and the second and last relative minimum, so you have going past x at 2 and approaching x at 4. Okay, and again, for those intervals we have, again, just for those exit values, again, we maintain the use of parentheses throughout. All right. Okay, now for what we have regarding operations between functions, and we have say just for the first part here. Okay, so we got so you have given functions f of x, g of x, h of x, as well as k of x. Now, in the case of what we have with numbers 8, 9, and 10, okay, so we are involving, okay, the functions g and h. And in the case of what we have with number 8, okay, so you have g plus h of 5. Okay, and so I'm looking at a specific case, so g plus h of 5. Okay, now this would come out to g of 5 plus h of 5. And if we go ahead and determine what g of 5 and h of 5 are, so again we have g of 5 to determine g of 5. Okay, so you have referencing g of x with x at 5. So g of 5 is going to translate to 5 minus 7. And 5 minus 7 is equal to -2. Now for h of 5, we're referencing h of x. So h of 5 is equal to 5 squared plus 5. Now 5 squared is 25, and 25 plus 5 comes out to 30. So going back to what we have for the sum function, g plus h of 5, so we have g of 5 is going to be at -2. And we have plus h of 5, which again is going to be at 30. Okay, so you have -2 plus 30. Okay, so this sum comes out to positive 28. Okay, now for what we have in the case number 9, still working with g and h functions. Now we have h minus g of 7 and expanding. Okay, so this will become h of 7 minus g of 7, and just with the x specified at 7, we can determine go ahead and determine the values of h of 7 and g of 7. Okay, so you have our h of 7. So we have 7 squared plus 5. Now 7 squared is 49. 49 plus 5 comes out to 54. As for g of 7, again, so referencing g of x, so g with x at 7, so you got g of 7 is equal to 7 minus 7. And so that is going to be negligible. And now taking the difference, so we have an h of 7. Okay, so I'm going to have 54 you got minus 0. So for h minus g of 7, okay, this will come out to 54. Right. And for number 10, okay, so this time we have g times h of 5. Okay, so again we'll have g of 5 times h of 5. Okay. And again, we're going to have this bit of history to repeat. So g of 5 is equal to 5 minus 7, which is negative 2. And h of 5, okay, we have 5 squared plus 5, which is 25 plus 5, which will come out to 30. Okay, and so we have with g of 5, okay, so we're looking at negative 2 times 30. And for this result, okay, we have the product at negative 60. All right. Now, doing a little bit of a change up. Okay, so for 8, 9, and 10, I've been involving exclusively variations of the functions g of x and h of x. Now, for 11, okay, I'm now throwing in the function f. Okay, now for f over g of 2, okay, so for f over g of 2, so I have f of 2 over g of 2. Okay, and just specifying the values. Okay, so with f of 2, okay, so I'm referencing f of x. So with x at 2, I'm going to have 3 over 2 plus 4. So this is going to be 3/6, which is going to be equal to 1/2. And as for g of 2, again, so you have g of 2 is going to be 2 minus 7. And so that will come out to negative 5. Okay, so by placing the inputs that are specified, so we have a little bit of a complex fraction. So we have 1/2 all over negative 5. And if I were to expand on out, okay, so I'm going to have 1/2 divided by negative 5. And if I divide by a number, say involving fractions, okay, so if I divide by a number, it'll be the same as multiplying by its reciprocal. So we have 1/2 times -1/5. And for the output, so a positive divided by negative is a negative. Same thing with a positive times a negative. So we have a negative. 1 times 1 is 1, and 2 times 5 is 10. So for 1/2 divided by -5, this will come out to -1/10. Okay. Now for what we have in the rational function, okay, here we have g over k of 0. Okay, so this is our first item with the function k involved. Okay, so you have g over k of 0. Now for g of 0, okay, so g of 0 have 0 minus 7. So this will come out to -7. And for what we have in the case of k of 0, so you got k of 0, so you have this radical function in the form of the square root of x plus 9, and with x at 0, so we have 0 plus 9, and the square root of 9 is equal to 3. So for g over k of 0, again, so we have g of 0 all over k of 0. And once again, so you have g of 0 is at -7. And k of 0 is equal to 3. And I got -7 over 3. And that ratio is already in simplest form. They could say -7/3, -7 over 3 as it is here, or 7 over -3. Okay, so any variation is the equivalent of -2 1/3. All right. Now, where we have the compositions at specified inputs to be of concern, and we have here. Okay, so we got okay, so we have in the case of number 13, okay, so you have the composition. We have f composed with g of 3. All right, so we have in 13. Okay, so technically you're starting out with f composed with g of 3. And again, the compact notation, again, we have as it's presented. Okay, we have f of g of 3. Okay, now we're going to operate in line with f of x is equal to 3 over the input plus 4. Now with input at g of 3, okay, so you have 3 all over g of 3 plus 4. Okay, and for what we're going to have here, we're going to determine, okay, just what g of 3 is going to be. Okay, so just kind of taking what we have to the side. Okay, so you have for g of 3. Okay, so we are referencing g of x. So we have g of x is x minus 7. Okay, so g of 3 is going to be 3 minus 7. And so that is equal to -4. Let me just put this over here. So this will come down to 3 over -4 plus 4. And guess what? We have 3 over 0. So for this particular composition, okay, for rational expression, I cannot have a zero denominator. And if I do, well, the composition, including this one, is going to be undefined. And for what we have, say for the composition in number 14, so I'm still using the same functions, but I have a reverse sequencing in the composition. Okay, so we have, in the case of G composed with f of 3, so yeah, with the compact notation, so we have G of f of 3. Let me do something. I'm just going to clean up this other stuff too. Okay, so for G composed with f of 3, so I have G of f of 3 okay, so we'll operate in accordance with G of x. So we have for G of x, okay, that is equal to x minus 7 and so for what I have here with the input at f of 3, so this is going to be f of 3 minus 7. Okay, and for f of 3, okay, so for f of 3, again, f of x is equal to 3 over the input plus 4. So f of 3, this will come out to 3/7. Okay, and so we'll have 3/7 minus 7. And in fractional terms, okay, so I'm going to have 3/7 minus, okay, you think of 7 as like the fraction 7 over 1, and putting in terms of sevenths, this is going to be 49/7. Okay, so for G composed with f of 3, okay, we're going to have a defined value, and this will come out to the negative difference where we have minus 46/7. All right. Now, where we have in the general case, all right, so we have for the domain of the various compositions, okay, and for what we have in the case of number 15, okay, so for 15, okay, we have f composed with h of x. And for the compact notation, so I have f of h of x. Again, the follow-through operation will be in accordance with f of x. So you're going to have f of the input is equal to 3 all over the input plus 4. Now for f of h of x, so h of x as the input. So replacing h of x with the expression to which that function is set equal. Okay, so we have 3 all over what's going to be x squared plus 5 followed by the addition of 4. And so once I lump together the x squared and the constants, okay, this will come out to 3 over x squared plus 9. Okay, so this is going to be your output in the case of f composed with h of x. Now, where the domain is concerned, so for the input, okay, so the input, again, we have h of x equal to x squared plus 5 and since we don't have an even root radical or a fraction from h of x, okay, this one has no restriction. Okay, now for the output, okay, we got a fraction with 3 over x squared plus 9. Okay, and this will be sort of a special case here. Now we got a ratio, and again, we have an x expression in the denominator. Now we have the x squared plus 9 cannot be 0. Okay, and if I try to find out, okay, what is going to be left out, say if I'm, okay, now I can factor a difference of squares with, if I had x squared minus 9, this would factor out to x plus and x minus 3, and you'll have 2 exclusions from the domain with negative and positive 3. However, with the sum of squares, if I isolate the x squared, say I have that x squared cannot be equal to negative 9, and if I take the square root property of equality that we have with the not equal separating the positive and negative square root terms as opposed to the equal, and we have the x cannot be equal to plus or minus the square root of negative 9. So I have the x cannot be plus or minus 3i. But here's the deal on this one. Okay, thanks to what I have with I, it turns out that there are no real valued exclusions. And since I don't have any real values excluded, okay, that means that the output is also going to have no restriction in terms of what I can work with from the real numbers. So anything that x is not allowed to be, it only comes from the set of complex numbers. So the input has no restriction and the output also has no restriction. And again, restrictions referring only to the set of real numbers. Okay, so for this composition, okay, we have no restriction at all. So that means that for the domain in problem 15, that is going to be the set of all real numbers. All right. Now, for the case in number 16, okay, so we're looking for the domain of G composed with K of X. Okay, so for G composed with K of X, again, if I start out with the composition notation, okay, so you have G composed with K of X, and this is going to lead into the compact notation where I have G of K of X. Okay, and so the outside operation, okay, we have with G, and again, so G is defined where we have G, the input is equal to the input minus 7. And here with the input at k of x, okay, this is going to be equal to k of x minus 7. And just filling in the expression that defines k of x, so we have the square root of x plus 9. And we have the square root of x plus 9 followed by the subtraction of 7, and these terms will be kept apart. And I cannot combine the 9 and the negative 7 because negative 7 is a standalone constant and 9 is locked inside the square root. Okay, so this is going to be the output. And in the case of looking for the domain, okay, again, with compositions of functions, okay, we have one restriction potentially will come from what is disallowed, okay, for the input function. Now for the input, again, you have k of x is equal to the square root of x plus 9. And again, because you have the square root, x plus 9 cannot be negative. Okay. Now it can be 0 or positive. And since I don't have x plus 9 situated as a fraction, so I have x plus 9 is greater than or equal to 0. So we have for this restriction, then we have the x is greater than or equal to negative 9. And guess what? For the output, the only restriction comes from the square root of x plus 9. So the output, again, because of the square root of x plus 9 and keeping x plus 9 from being negative, again, you have that restriction. By the input restriction, that is going to be x is greater than or equal to negative 9. So for this composition, then we have the only restriction is going to be that x is greater than or equal to negative 9. And so for what we have for the domain, okay, just looking at it visually. Okay, so you have again the central piece of value we have with negative 9, and for the dynamic now we have negative 9 is included thanks to the equal sign. So we have a solid point, and everything else is going to be greater than. And so we're going to have a ray that is going to go out to the right. And so in the case of the domain of G composed with k of x, again, we're going from and including negative 9. So negative 9 is going to be in the brackets. And we have going out toward infinity. Okay. Now, for numbers 17 and 18, now we are involving the same individual functions. Okay, so for 17 and 18, okay, you're looking at the domain of f plus k of x, and at 18 we're looking at the domain of f over k of x. And what I'm going to do here is just kind of do sort of a broad stroke. Now for f of x, again we have 3 over x plus 4. And k of x, again I have the square root of x plus 9. Okay, now, with the sum difference in product functions, okay, you're going to have the same domain. Okay, again, for f of x, we got 3 over x plus 4, so the denominator, x plus 4, cannot be 0. So we're going to have the x cannot be equal to negative 4. And again, just with k of x earlier, again, x plus 9 cannot be negative, and again, so we have x has to be greater than or equal to negative 9. Okay, now for the domain of the sum difference in product functions, again, for the sum difference in product functions only, the domain will be defined by the combined restrictions of the individual functions involved. So we have the x cannot be negative 4, and also to be able to work with k of x, not g of x, but k of x. Okay, so for k of x, to be able to work with k of x, you have x is greater than or equal to negative 9. Okay. Now, in terms of the overall framework, in terms of what we have situated. Okay, so if I were to graph these restrictions, okay, so I got negative 4 and negative 9 excluded. Okay, so again, negative 9, you have x is greater than or equal to negative 9. So negative 9 is included, so I'm going to have a solid point. Okay, and if I had just x is greater than or equal to negative 9, I would have an array going continuously out to the right. But instead of having continuous motion as we proceed past negative 9, we have to stop right here because x cannot be negative 4. So negative 4 is excluded. So x cannot be negative 4, and I have x equal to negative 9, and the other portions will be those other values of x that will be greater than negative 9. Okay, so we have, just taking what we have here, so I'm going to have a line segment connecting negative 9 to the hole that we have at negative 4. Now for the rest of the activity, so we have a ray that's going to go out to the right. And that is going to tend to infinity. Okay. And just for the sum difference in product functions. Okay, so just for number 17, for f plus k of x, now we have for the domain, Okay, so there's nothing going out in the direction of negative infinity. So the activity is going to begin from and including negative 9. And we have approaching but not including negative 4. So negative 4 is going to be bypassed. And for the rest of the domain, okay, we have going past negative 4. And we have approaching infinity. Okay, so in the case of 17, okay, so you have this domain in the layout. And again, the domain of the sum function is going to be the same as what we have for the difference and the product functions. Now, for what we have in the case of f over k of x, okay, so again we have f of x is equal to 3 over x plus 4 k of x. Okay, we're going to have the square root of x plus 9. Okay, now for f over k of x, again, I still had to be able to work with both f of x and k of x. And for f over k of x, so I have f of x over k of x. And we have for f of x, again I have 3 over x plus 4. And for k of x, I have just the square root of x plus 9. Okay, so you have a little bit of a complex fraction. So I have 3 over x plus 4. So you have divided by the square root of x plus 9. And so you have 3 over x plus 4 times the reciprocal of the square root of x plus 9. And if we combine together, okay, so this will come out to 3 over, and you have the quantity of x plus 4 times that, okay, of the square root of x plus 9. Okay, and so for what we're going to have here, okay, so I'm going to have to keep both f of x and k of x defined. Okay, so again, we have with 3 over x plus 4, this is already presented as a fraction. And even though f of x is in the numerator, I still have a fraction in the numerator, so the bottom part of that fraction cannot be 0, so I still have that x cannot be negative 4. Again, so you have x plus 4 reappears at the end, so I still have the x cannot be negative 4. Now, with k of x, I have the square root of x plus 9, and this is in the denominator. And it's going to stay in the denominator. And so we have with the square root of x plus 9, because we have a square root. Once again, x plus 9 cannot be negative. And because we have the denominator. In the denominator case, so x plus 9 cannot be 0. Okay, so that means, okay, so I have to keep k of x defined, and now that k of x was situated in the denominator. And we have that not only can x plus 9 not be negative, but also it cannot be 0. So x plus 9 must be positive. So we want to have x plus 9 is greater than 0. And so we have, for the outcome here, we have the x is greater than negative 9. So for what we have in the overall picture, okay, so we have with the restrictions, again, to keep f of x defined, x could not be negative 4. And to keep the function defined where k is concerned, you have now situated with the square root of x plus 9 as an even root radical term and also as the denominator. So again, we have that x must be greater than negative 9. And so for what we have in the case of the domain, it's got negative 9, negative 4, and this time where the sum difference and product functions were inclusive of negative 9, we're going to have it to be exclusive of negative 9 for the quotient function. So you have excluding both negative 9 and negative 4. And we have in terms of the activity, you have, again, x is greater than negative 9. Again, but leaving out negative 4. Then we have proceeding past negative 4, and we've got array going continuously out to the right. And so while the domain of the sum difference and product functions comes out to these sets, it is with the domain of the quotient function that we're now going to have negative 9 excluded. It's almost the same thing as the domain for the prior 3 operations, but instead of a bracket, then we have a parenthesis around negative 9. So you have going past negative 9, approaching but not including negative 4. And for the rest, you have those values of x that will be greater than negative 4. Okay, so for this last problem, okay, that is going to be the final result. Okay. And